Welcome to MetaGet, everyone. Today we are going to basically talk about iron making. So this is our iron making class, and we are starting it now. So first and foremost, before I start the class, like I would like to just so sir. Okay, so let us start the class. So first and foremost, we need to understand that why this subject is important. So if I talk about iron making, right? So like why this subject is important? Because the iron that we use in our day-to-day life, we do not get the iron in this form that we see. So in the ore, it is in the form of hematite, mostly in the form of hematite. Sometimes magnetite ores are also present. So what we get is basically in the ore Fe2O3 hematite, right? From here, actually, in the process of iron making, it is basically nothing but it is a reduction process. So we reduce it to pig iron, and then after the iron making process is complete, then starts our steel making process. But here we will be basically focusing on the iron making process itself, right? So first and foremost, I would like to start the class with by focusing on the difference between what is the difference between iron and steel. This would like to first focus on. Then we will define, we will see what is meant by iron making. So I'll talk about the definition of iron making. We'll see what is iron making, and then we will talk about the basic thermodynamics of iron making. What is the basic thermodynamics which is linked, right? So we'll see this. First, let us take up the first question, that what is the difference between iron and steel. Now, we all know that what is steel? Steel is nothing but it is an interstitial solid solution of carbon in iron. So when we add carbon, so steel is predominantly, it is iron only. But when we add carbon in it, so there are certain voids, and when the carbon get into the in those voids, like in the interstitial voids, it strengthens the material that we basically call as steel. So steel is nothing but it is an interstitial solid solution of carbon in iron. So maximum carbon in steel, I can say what is the maximum carbon percentage in steel. The maximum carbon percentage in steel is basically 2.1%. And if the carbon percentage is it overshoots or goes beyond 2.1%, when it goes beyond 2.1%, we will call it basically cast iron. Will not call it steel, it becomes cast iron when the carbon percentage is more than 2.1%. Okay. Now, why we add carbon? What is the main purpose of adding carbon in steel? Because you see, the pure iron, if I talk about the pure iron, it is not, its strength is not that much. Still, its strength is much improved, okay, compared to pure iron. So that is the basic idea of adding carbon in iron. So the as we increase the weight percentage of carbon, the hardness of the material also increases. The hardness of the material also increases, right? Now, let us come back to the topic of to our main topic, which is iron. Now, like I said, that the iron that we get, or that we use in our day-to-day life, in the nature, it is not in this form. In the nature, in the ore form, you get this, which is mostly hematite. This is hematite ore. And with the ore, in the mineral dressing process, we have already talked about it, that ore is not pure. So it has got a lot of gangue materials. So what are these gangue materials? These gangue materials are nothing but these are the unwanted materials. The materials that we don't want. But invariably, we cannot help it. These materials will be there anyway. So what are these gangue materials? They are like P2O5, okay, MnO, manganese oxide, okay, there will be silica also, SiO2, and things like that. So all these unwanted materials are also present. Now, you see, our main purpose of iron making in this subject, we will focus on how to extract the maximum of iron from this hematite ore or from the ore and remove these gangue materials. Okay, so our main purpose or the focus is going to be to get or to extract iron, maximum iron from the ore, and to basically to separate out the gangue materials. Okay, so generally, if I talk about a good quality hematite, so total iron in hematite is, so I'm talking about good quality ore, total iron in hematite, it is generally within the range of 62% to 65%. This is for good quality hematite. Okay, now we reduce it. This is Fe2O3. So in the process of iron making, what we do, the iron oxide can be effectively reduced by carbon. So iron oxide, we would like to reduce the iron oxide or Fe2O3. Iron oxide can be effectively reduced by carbon, right? But this can only be done at high temperatures. We need quite high temperature in order to reduce the iron oxide using carbon. Why we need high temperature? We will see that. All the concepts will be covered. And this process is basically called carbothermic reduction. This is nothing but carbothermic reduction. Right? So why carbothermic? So if you just see this, if you just see this, I mean this word, carbothermic. So we are using carbon as well as we are also employing high temperature. So there is a thermic turn because of that. So iron oxide is being reduced by carbon at high temperature. So we will call it carbothermic reduction, right? Now, I tell you, suppose now we are giving two cases. What are these two cases? In the first case, suppose we are actually employing oxide of iron, that is the iron oxide ore. Iron oxide ore we have taken, and we have taken carbon, right? Now, when the temperature, what temperature actually, how much temperature? Suppose minimum 1000 degrees Celsius has to be given. Okay. Now, if you reduce, if you add carbon in the iron oxide ore at about 1000 degrees Celsius, you will get solid product of iron plus gangue, right? So you will get semi-solid product, not the solid product, it is basically semi-solid product. Semi-solid product of iron plus gangue. So there are gangue materials also. Where will these gangue materials go? We talked about that earlier in our previous slide. We saw that this Fe2O3 hematite, it is there. But along with this hematite, there are gangue materials also present. Good amount of gangue materials are present. Now, when you are actually reducing it with carbon, these gangue materials will, if I just give only the carbon, then what this carbon will do? This carbon will reduce the iron oxide, convert it into iron. You will get a semi-solid product of iron. But where will these gangue materials go? These gangue materials will go into this iron only. Okay, so iron is in the solid or semi-solid state and gangue is mixed with it. I can say that here we will not get our iron which we intend to get. The iron which we intend to get, that purity of iron we will not get here. Okay, try to understand that. So here iron is basically, I can say, here iron is mixed with gangue materials. Right? So iron is going to be, it is going to be mixed with gangue materials. But now I take another case where I am using the same iron oxide. We are giving the same iron oxide ore we have taken. Carbon, yes, we have given carbon. Along with carbon, we have added some flux. Okay. And the temperature, now we are suppose giving, we have increased the temperature to about 1400 degrees Celsius. Now what we will get, the product, you see, just I would ask all of you to focus on the product, what we are getting. Like when in the first case, we have not used the flux. Flux was not used. Iron oxide directly and carbon was used and temperature was required. That was required was basically about 1000 degrees Celsius. We got semi-solid product of iron and gangue was also present. Gangue was present in the semi-solid product of iron. So purity of iron was less. But here when we are using the flux and we are increasing the temperature a bit further, like 1400 degrees Celsius, what you will get? You will get liquid iron plus liquid slag. Because of addition of this flux, what extra thing that we are getting? The extra thing that we are getting is this slag. The slag is coming into the picture. So this slag we are getting, right? And the gangue materials that were there, the gangue materials are getting into this slag. Okay. most of the gangue materials will go into the slag phase, and the purity of iron is going to be more just because of addition of the flux. So when flux is added, the gangue is separated as liquid slag. We can say that when flux is added, what happens? The gangue is separated as liquid slag. Right? Now, composition of liquid metal or hot metal that we will get. Like we are talking about now that okay, we are taking the iron oxide and we are using carbon. Okay, we are reducing it by using carbon at high temperature, and okay, we have also added flux. All this we have seen, like iron oxide plus carbon plus flux. Okay, at higher temperature, 1400 degrees Celsius, suppose, and what you will get the hot metal plus slag. So this is now we will talk about the composition of this hot metal. What is going to be the composition, or what is this is something not fixed, obviously. It will depend upon the process or the route. So this is not something which is fixed. We can say that yes, 100% the composition is going to lie or is going to be exactly this, but it will be in that range that we will discuss. The range of the composition, mainly when we talk about composition, always remember we always talk about range. Okay, so composition of liquid metal or the hot metal. So that is the iron that we are getting after the process in the blast furnace. Okay, that we call as the liquid metal of the hot metal. Okay, so that is exactly what we call the hot metal. Now, let us see. Okay, so if I'm talking about the composition, you see, it is about 5% carbon, 5% carbon, 1.5% silicon. So silicon is going to be quite high, 0.4% phosphorus, and 0.05% sulfur. So this is typically the composition: 5% carbon, 1.5% silicon, 0.4% phosphorus, and 0.05% sulfur. Okay, so as we reduce the iron oxide, silicon and phosphorus are also reduced. So you see what is happening, why these elements are coming into the picture. Why? You see, because in the process, so first and foremost, let us understand why carbon is coming. Carbon is coming because the entire in the reduction process only we are adding carbon. Okay, so carbon is there in the reduction process only. So I have added carbon. So this carbon will inevitably seep into the hot metal or will go into the hot metal. So why carbon is coming, that is quite clear. Now, a lot of in the gangue materials, we had SiO2, silica. It was present in the gangue materials. Now, as silica was present in the gangue materials, so SiO2 is also getting reduced. Silica is getting reduced to silicon. Okay, silica is getting reduced to silicon. And obviously, some silicon is going to get into the slag, but some will also get into the hot metal. So that is why 1.5% silicon is coming from that. Similarly, phosphorus was also present in the gangue metal in the form of P2O5, phosphorus pentoxide. So from that P2O5, okay, some of the phosphorus is going to get reduced, and some will go into the slag phase and some will get into the hot metal. Likewise, sulfur. So basically, see, I can say that when we reduce the iron oxide, silicon and phosphorus are reduced. Silicon from SiO2, silicon from SiO2, and phosphorus from P2O5, phosphorus from P2O5. Okay, they will come into the hot metal. And because when they see what happens is they come into the hot metal, this we have understood. And also the temperature is quite high. So temperature is quite high here. Now, because of this high temperature, what is going to happen is the diffusion is going to be more. Okay. So as the temperature is high, the diffusion rate is also high. Okay. So we know that diffusion depends upon the temperature. So as the temperature is high, so they will diffuse more. They will diffuse more or faster. Okay. Into the hot metal. So that is the thing. Okay. So this was mainly the idea. Now, after this, we will understand some basic thermodynamics of iron making. So, what is the main thermodynamics of iron making that we need to understand? Now, when I talk about the basic thermodynamics of iron making, okay, one thing that comes into the mind immediately that should come into our mind is the Ellingham diagram. So, this diagram, what is this Ellingham diagram? Actually, this Ellingham diagram is nothing, but it is a diagram or a graph which tells us the relative stability of the metal oxides. Okay? Relative stability of the oxides mainly, not only metal oxides. I can say that it talks about the relative stability of the oxides. Okay? In the y-axis of the Ellingham diagram, we put the delta G naught. That is the delta G value. Delta G means the Gibbs free energy. So this is we take as we consider it as the Gibbs free energy of formation. And in the x-axis, we plot the temperature. In the x-axis, we plot the temperature. Now, if you look into the Ellingham diagram, you will see that there are many oxide curves that are there in the Ellingham diagram. Many curves of the oxides that are there in the Ellingham diagram. Okay. Most, most, most of the metal oxide curves, their slope is basically positive. Positive means, see, I am drawing some of the metal oxide curves. The thing is going to be, so this is silicon. This is the curve for silicon plus O2 gives us SiO2. Okay. Similarly, suppose another curve we have drawn, something like this. And this is the curve for manganese plus O2 giving us MnO. While writing this equation for the Ellingham diagram, always remember one thing that 1 mole of oxygen should be used. So every time we will be using 1 mole of oxygen only because that is the basis of calculation of the delta G value, right? So we have here, this is the curve for the manganese oxide. This is the curve for the silicon oxide. Okay. Now I tell you, we'll explain the things. Suppose another metal oxide curve I am drawing, which is nothing but we can say the curve for iron oxide. Like we can say this is the curve for 4 by 3 of iron plus O2 giving us 2 by 3 of Fe2O3. Okay. So this is the curve for iron oxide. Now, so the idea is, what I want to tell you here is that you see most of the metal oxide, there are many metal oxide curves. I am not taking all into consideration. You can look into the Ellingham diagram. So the main idea is that metal oxide curve, which will be lower into the Ellingham diagram. Lower means at the, say for example, if I am comparing between MnO and SiO, if I am comparing between manganese oxide and silica, SiO, then silica is lower compared to Mn. Obviously, from the graph, you can say that silica is lower compared to Mn. That means the silicon oxide or silica is more stable compared to MnO because it has got more negative delta G value. These delta G values are always negative. So this axis is entirely the negative axis. Okay. So we can say that it has got more negative delta G value, and we know that from our basic thermodynamics or whatever you say from our basic knowledge of chemistry, you know that the less the delta G value, more stable is going to be that material. So I can say that silica is more stable compared to MnO. Similarly, at any temperature. Similarly, Fe, uh, MnO is more stable compared to Fe2O3 at any temperature. Okay. Now you see that there are two lines which are very, very important and which we need to understand. One line is this. What is this line? This is 2 times of carbon plus oxygen giving us 2 times of CO. Okay. So this is the line for the carbon monoxide. Okay. And if you look at this line, how is the slope of this line? The slope of this line is basically downward. Okay. So it is sloping downward. That is how the slope is. Okay. So it is basically negative slope, I can say. Now, as the slope is negative, what it indicates is that with more and more rise in temperature, see, with more and more rise in temperature, that means as the temperature we are increasing, because this x-axis is the temperature. So if you go along the positive direction of the x-axis, that means you are increasing the temperature. So from this negative slope, we can say that as we increase the temperature, the carbon monoxide becomes more stable. Because you see the delta G value of the carbon monoxide of this line, yeah, the delta G value of the carbon monoxide is decreasing as we are increasing the temperature. It means that carbon monoxide is becoming more stable as we are increasing the temperature consistently, right? But which is not true for most of the metal oxides. If I talk about SiO2, you see, as I am increasing the temperature, the delta G value is decreasing. That means SiO2 is becoming less stable. Okay, SiO2 is becoming less stable with rise in temperature. Similarly, MnO, because it is having a positive slope, that means with rise in temperature, the delta G value is also increasing. Okay, so as the delta G value is increasing with the rise in temperature, so MnO, I can say MnO is becoming less stable with rise in temperature. Similar for Fe2O3 also. But this is I can say an exceptional curve, the CO curve. Okay. And another curve which will be our point of interest is going to be this curve, which is more or less horizontal. That means it will seem as if that this curve is not having any impact with respect to temperature. This is the curve for carbon plus oxygen giving us CO2. This is the CO2 curve. Okay, this is the CO2 curve. Right? Now we will see what happens. If you look at this curve, like Fe2O3, this curve is Fe2O3, right? And if you look at this, I mean, if I tell you that, okay, Fe2O3 is there and look at CO curve, look at the CO curve. They are intersecting at some point. They are intersecting at some point. What is that temperature? If you find out that temperature, at what temperature the CO curve is intersecting with Fe2O3. Okay, suppose the temperature is, you say that, suppose we are saying it is 1200 degrees Celsius. Now, that means in order to reduce Fe2O3 with carbon, okay, you need at least 1200 degrees Celsius. If your temperature is less than 1200 degrees Celsius, then you see your Fe2O3 is more stable compared to your CO, carbon monoxide gas. Then CO will not form. Then CO will not form. Then what is going to happen? Fe2O3 will remain as Fe2O3 only. Carbon cannot reduce Fe2O3. At that, if you are not bringing the temperature high enough. But when we bring the temperature high enough, when, so this is the, suppose this is the point of intersection. Up to that temperature we need to heat. Now when you go above that temperature, you see what happens. Your CO line has become more stable. So your CO line has become more stable means that now the carbon can easily reduce the Fe2O3. Now can you understand from this that why high temperature is required? Why high temperature is required? And also another thing which is very important here is, if you look at this CO2 CCO2 line as well as CCO line, means the yellow line and the green line I have drawn. So if you look at it, then they are also intersecting at some temperature. Okay, this is the point of intersection. Now, whatever be the temperature, I am not concerned about that. It may be 1200, maybe 1300 or something. But the point is, you need to understand one, that if the temperature is T, if the point of intersection of the CO line and CO2 line, if they are intersecting at a temperature, suppose T temperature, they are intersecting. Now, if my temperature is less than that temperature T, okay, then which is more stable? If I ask you, which is more stable? CO is more stable or CO2 is more stable? At a temperature less than the intersection temperature, which is T, you will say that definitely CO2 is more stable because it is having a less del G value compared to CO, because you see the CO is above when the temperature is below the intersection temperature. But whenever I am going above that intersection temperature, that is whenever I am crossing that intersection temperature, at that time, what is happening? My CO is becoming more stable. So at that time, carbon will have a tendency to get converted to CO directly, carbon monoxide, because carbon dioxide is no more stable at higher temperatures. So carbon dioxide will break into carbon monoxide at higher temperatures. So at higher temperatures, you will get more and more CO compared to CO2. Okay. So this is also a very important concept that we have seen. So like we have discussed about Ellingham diagram. Now we will try to write whatever we have discussed. We will write some of the key points So key points about Ellingham diagram. Key points about Ellingham diagram. First is the stability. Ellingham diagram. It talks about the stability of oxides. It talks about the stability of oxides. How it talks about the stability of oxides? The lower a line is on the diagram, the more stable is its oxides. We have seen that the lower a line is on the diagram, the more stable is its oxides. Right? This is number one. Because a more negative del G value means the oxide is harder to reduce. You can write this. A more negative del G naught value, it indicates or it means the oxide is harder to reduce. Okay? Number one. Number two, it talks about feasibility of the reduction. It talks about the feasibility of the reduction as well. Now, if the line for a reducing agent lies below the oxides line at a given temperature, the reduction is thermodynamically feasible. Say, for example, I want to reduce Fe2O3. Then minimum temperature which I should give is greater than this temperature, which is the intersection temperature. This is the intersection temperature. So minimum I should give a temperature which is greater than this temperature T, because only then the carbon can reduce the Fe2O3. So exactly that is what we are seeing here. So if the line of the reducing agent, you can write, if the line for a reducing agent like carbon monoxide, aluminium lies below, if they lie below the oxides line at a given temperature, okay, the reduction is thermodynamically feasible. The reduction is thermodynamically feasible. For example, at 1000 degrees Celsius, the line for carbon and carbon monoxide lies below FeO. Okay, so that means that iron, so FeO can be reduced by carbon, and minimum temperature that we have to give is basically 1000 degrees Celsius. Below 1000 degrees Celsius, if I am talking about just FeO line and the your CO line, then below the 1000 degrees Celsius, carbon will not be able to reduce. Carbon will not be able to reduce the Fe. Okay. And another very important concept that we are, or maybe not a concept, but conclusion that we can draw from the Ellingham diagram is that most oxides become less stable at higher temperatures. Most metal oxides become less stable at higher temperatures. Right? Except there is one exception, except CO, carbon monoxide. Okay? Because we saw that CO becomes more stable at higher temperatures. Okay. Okay. Now, there is a question. We can ask one thing that we can also use silica like SiO. Like if you just look at this Ellingham diagram, then you can definitely say that okay, with rise in temperature, definitely. See, this is the line for our iron, iron oxide, Fe2O3 line, and this is the line for SiO. Now you can say that obviously at higher temperature, these will also intersect. So instead of using the carbon, we can use also silica. But you see, if we use silica, there is going to be a problem. That is, yes, SiO2 is a very stable oxide. So it is going to reduce the iron at a very, very high temperature. So the temperature that actually you need in order to reduce the iron is going to be quite high. Okay. And if we use the silica, that is the SiO2, it forms solid slag and it becomes difficult to separate. Once the solid slag is formed, it becomes difficult to separate. But when we use uh, this one, the carbon, then carbon, you see what is happening as in the product, we are getting CO. And this CO is in the gaseous state, carbon monoxide. Okay, so it is automatically removed. Okay, very easily it can be removed, right? So this is the main thing. Now, so this you have understood. Okay, just a minute. Now we will talk about something very important, which is the heart of iron making. And what is it? It is called the iron making blast furnace. Iron blast furnace. So all the reactions of the iron making, whatever reactions we will talk about here in this subject, in this course, in today's lecture, everything happens inside the blast furnace. So we need to understand first the shape of the blast furnace, shape of blast furnace. We need to understand after that, after understanding the shapes and the aerodynamics of blast furnace, we'll be talking about the zones of blast furnace, zones of blast furnace on longitudinal cross section. we'll be talking about the zones of the blast furnace on the longitudinal cross section. And then we will also be talking about reactions in blast furnace. What are the various reactions that are taking place inside the blast furnace? Okay, on longitudinal cross section. So all these things we will basically talk about. Okay. First and foremost, let us see what is how the shape of the blast furnace. If you are asked to draw a blast furnace, typical shape of the blast furnace is something like this. So, next. See, this is typically the shape of the blast furnace. So, what are these? Why the shape of the blast furnace is like this? We will talk about. So, it is from this is the top or the mouth of the blast furnace, from where all these charged materials, the materials are charged in. Okay. And it is tapered outward. From this, if you see, it is tapered outward. Okay. So this is called the throat. This is called the throat. And this is the top cone. So throat, what happens? Final burden distribution device is basically at the throat. And this section, which is tapered outward, this section of the blast furnace is what we call the shaft. This is called the shaft. And in this shaft, in this section only, most of the reduction reactions takes place. Most of the reduction reactions takes place in the shaft only. So that is why you see the shaft is an extensive region, is more, very much, means is a broad region, I can say. Because most of the reduction reactions are getting completed in the shaft. Okay. Now, followed by the shaft, uh, there is this region, okay, where the slope is becoming vertical, like this. So this is called the belly region. This is the belly region. And what happens at this belly region? Okay, the solid softening starts. Okay, so solid softening start means you see the charge and everything that we have charged, like the coke, you see, you can say the coke, the iron oxide in the form of ores, the flux, whatever materials that you have charged into the blast furnace, they were in the solid form. Okay, they were in the solid form. But as you are descending down, always remember that ultimately inside the blast furnace, what happens is the lower region of the blast furnace, it is at a higher temperature compared to the upper region. Obviously, because upper region is this top cone, this is like this is at the room temperature only, na? Because we are all the materials that we are charging it from the top cone. So that is equivalent to the room temperature, the materials that are being charged. Then what is happening? What is happening? The materials are getting inside. Okay. And as you descend down the blast furnace, okay, your temperature slowly, your temperature is going to rise as you descend down the blast furnace. And this is very, very important to understand. Okay. Now, let us see now what happens. So this is the belly region I'm talking about. So in the belly region, what is happening? The solid softening starts because higher temperature is there. As we are coming down, higher temperature. So solid softening starts. Okay? Solid softening starts. That is, the solid materials, they are now softening. Okay, softening means they are becoming liquid. Not liquid, semi-solid, jelly-like substances. And after the belly region is the Bosch region. This is the Bosch region. This is called the Bosch. Tapered inward again. This was tapered outward, now it is tapered inward. This region is called the Bosch. Okay. So this is the region where solid is basically getting converted into liquid. Solid is getting converted into liquid at the Bosch region. And finally, this is the hearth. Finally, this is the hearth. This region is called the hearth. 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 Now, what is happening at the hearth region? At the hearth region, basically, slag metal recovery is taking place. Slag and metal, they are getting separated. Slag metal, so we call it slag metal recovery. So ultimately, one thing you can understand, one thing is very important, what it is. To note from the SAIL exams point of view, now I'll tell you what is important. So you should know the name of these regions like shaft, belly, wash, hearth. You should know their sequence. Like if we are coming from the top to the bottom, first what? First is top cone, then throat, followed by the shaft, then comes the belly, then wash, and सबसे नीचे comes the hearth. So this is the sequence. This is the sequence. Okay. So sequence you should remember. And the shapes, obviously, the shape of the blast furnace, how it is, this you should remember. And another thing is that the reactions. We'll be talking about the reactions in just we'll be talking about the reactions. You see yourselves. So this is the thing. Some of the things that we should be focusing on. Now, another thing which is important is you see there are copper cooling plates. I mean, if I'm talking about this blast furnace as a whole, now there are copper cooling plates also. Okay. Those are called the staves, STAVES. So they are basically all around this. There are copper cooling plates. Now, let us see what happens in the shaft. Okay. So before the shaft, I talked about the throat. Before the shaft, we talked about the throat, right? So throat is this portion. If you see, this is the throat. Now what happens in the throat? Throat is the topmost region. You can say this is the topmost region. Throat is the topmost region. The shape is narrow opening. It is a narrow opening. That is top of the truncated cone. Okay. And what is the function? Main important is the function. The function of each and every part we must remember. So in the throat, it is nothing but the entry point of this is the entry point of the charge materials. So whatever materials that we are charging inside the blast furnace, that is we are charging it through this throat only. Okay. So these are the entry points of the charge materials. Okay. Okay. So this is the function. So what are the charge materials? You should also know about the charge materials. The charge materials are iron ore and limestone. Predominantly, these are the charge materials. Okay. And hot gases like carbon monoxide and N2, they exit from here. So you can also say that hot gases like carbon monoxide and dinitrogen, okay, they exit from. Okay. So sometimes has a bale or hopper system to prevent the gas escape. Okay, that thing. And what is the temperature? The temperature of this part is, the temperature of this top part is, it is about 200 degrees Celsius to 400 degrees Celsius. Now you can ask that from where this temperature is coming, because my reduction reactions are taking place downward. Okay. And but we are not from why the top part of the blast furnace that will have this temperature 200 to 400 degrees Celsius. That is because you see the gases are hot. These are hot gases. So in the when these hot gases will ascend upward, they will lose a lot of temperature. But even if they lose a lot of temperature, some temperature will be there. So that is why this top cone is having a temperature of 200 degrees Celsius to 400 degrees Celsius. This is because of the temperature of the gases. Okay. Now this was about the throat. Now we should focus about the shaft. Now if I focus about the shaft, this shaft is sometimes also called as the stack. This is also sometimes said or called as stack. Okay. Now, how is the shape? How is the shape? Let us understand or talk about the shape first. Right? So it is slightly widening downward. Okay. The shape is, I can say, it is slightly widening downward. Or tapered. Right? So that is the, see, this part we are talking about now. We are talking about the shaft, right? So shaft it is slightly widening downward. So that is why I call it taper. The what is the main function? Very important. What is the function? Function of this shaft part, right? Main function is, it is the main preheating and the reduction zone. Main preheating and reduction zone, right? So what are the reductions means reduction reactions that are basically taking place in the shaft? Primarily, most of the reduction reactions are taking place in the shaft only. Say for example, Fe2O3, if I'm talking about Fe2O3, Fe2O3 is getting reduced to Fe3O4. The steps also very, very important. So please remember, like the sequence I am showing, please remember this sequence. This is hematite and this is magnetite. So hematite is being reduced to magnetite. So Fe2O3 is reduced to Fe3O4. The Fe3O4 is further reduced to FeO, and the FeO is reduced to finally to iron. So if I directly write, or if someone directly shows you that Fe2O3 is directly getting reduced to iron, it doesn't happen like that. So it is not a direct reduction. Like Fe2O3 directly doesn't get reduced to iron. There are steps. First, Fe2O3 will get reduced to Fe3O4. Then Fe3O4 is getting reduced to FeO. And then finally, FeO, or the iron oxide, is getting reduced to iron. So these steps are there. And most of these reduction reactions are actually taking place inside the shaft. Okay, we need to understand. So most of this. And burden materials get heated. What happens? The burden materials get heated by upward moving hot gases. So whatever burden materials that we have given or charged, so burden in the form of iron oxide, or the ores, iron ores, burden in the form of our what you say, the limestone, and burden in the form of coke. So all these materials, what will happen? The hardened materials, they will get heated by upward moving gases. So the gas is the main source of heat inside the blast furnace, you can say. These gases, what is happening? These hot gases, they will impart the temperature as the gases will ascend upward like this. Okay, hot gases, they will ascend upward like this. These gases will come in contact with the charged materials. Charged materials means the burden materials. And these hot gases will impart their temperature, high temperature, to these burden materials. Right? So that is the point. So the temperature is basically about, what is the temperature? In this case, in the shaft portion, the temperature is about 400 degrees Celsius to 1000 degrees Celsius. This is the temperature in the shaft. Okay. Now I talk about the belly. After the shaft, we go into the belly. So belly is just below the shaft. It is just below the shaft. Right. So shape, how is the shape? How is the shape? Widest part of the blast furnace. So this also you should remember. So it is the widest part of the blast furnace. So if you have a blast furnace, like I show you, so this is belly. This portion is belly. So definitely you can see that why I tell this as the widest part of the blast furnace. Okay. Having the maximum diameter or the width. Okay. So this is the widest part of the blast furnace. And what are the functions? What are the functions of this part? If we talk about, it acts as a transition region between reduction and melting zones. It acts as a transition region, okay, between reduction and melting zones. Right? And softening and melting of the burden starts here and it becomes semi-molten here. Softening and melting of the burden starts here and burden becomes semi-solid. Okay. What is the temperature of this belly region? The temperature is typically 1000 degrees Celsius to 1400 degrees Celsius. That is the temperature. Okay. So after the belly region, what is there after the belly region? What is there after the belly region? It is Bosch. Which portion is Bosch? If I talk about the Bosch, this is Bosch, you see, tapered inward. So I think all of you can see that. The Bosch is tapered inward. So, so what happens in the Bosch? The furnace begins to taper inward inside the Bosch. And most important thing that take place in the Bosch is the combustion of coke takes place in this Bosch region. Right? So I can say the furnace begins to taper inward, right? And combustion of coke takes place here. Combustion of coke. So whatever coke that we are charging, the combustion of the coke is going to take place in this region. So combustion of coke takes place here. And coke means carbon. When it is getting combusted with oxygen, it will get converted to CO2. Okay. And another reaction that is going to take place is that the CO2 will come in contact again with carbon. And when the temperature is quite high, this is going to give us CO. So you see these two reactions that we have written here is very, very important. One is this reaction 1 and reaction 2. Why it is important? Now I'll tell you. Because always remember one thing, that is when these reactions are taking place, like the reaction sequence is always like this. Like carbon, it comes in contact with oxygen. Okay. Carbon comes in contact with oxygen. First, it is going to become CO2. First, CO2 ही बनेगा. Directly CO नहीं बनता है. So first, when the carbon come in contact with oxygen, it is going to form CO2. Now, what happens when the temperature is quite high? At a quite high temperature, if you look at this Ellingham diagram, why we gave so much time to the Ellingham diagram? Now you will understand it. If you look at this Ellingham diagram, at high temperature, what is happening? As the temperature is becoming high, the thing which is happening is that my carbon monoxide curve is more stable compared to the carbon dioxide curve. So at high temperature, carbon monoxide is more stable because the del G value for carbon monoxide is more negative at high temperature. That you can see from the Ellingham diagram itself. So what is happening at high temperature? This CO2, which is being formed, the CO2 will get reduced to carbon. Sorry, will get reduced to CO. CO2 will come in contact with carbon because some carbon will always be present because coke is there in the blast furnace. So because of the coke, because coke is there in the blast furnace, what is going to happen? The carbon dioxide will come in contact with the solid carbon, and at high temperature, it will get converted to CO. Okay, I think this part is clear. And last but not the least comes the hearth. Now, what happens in the hearth is like what happens in the hearth, basically, everything is in the liquid form, and hot metal and slag both are in the liquid form, the slag and as well as the hot metal. So, hot metal and slag, they are recovered at this region. Recovered means basically nothing but separated. So, they are separated in the earth region, right? So, this was the zones of the blast furnace. I think now you have a fair idea about the various zones, okay, of the blast furnace. Now, after this, we will talk about the we will basically focus more on the different kinds of zones in the blast furnace. We will focus more on the different kinds of zones in the blast furnace. First, we will talk about the dry zone. Okay. Then we will talk about wet zone. So there are basically three kinds of zones broadly, I can say. One is the dry zone, another is the wet zone, and another is what we call the combustion zone. Combustion zone. So dry zone means what? Dry zone is basically solid gas interaction takes place. So why dry? That is because you see solid and gas interaction is taking place. So where just solid and gas interaction is taking place, we will call that zone as dry zone only because there is no liquid. In the liquid zone, what happens? Sorry, in the wet zone, what happens? There is liquid gas interaction. There is liquid gas interaction. And in the combustion zone, what happens in the combustion zone? In the combustion zone, mainly carbon plus O2, it is getting converted to. So carbon coming in contact with O2, it is converted to CO2, carbon dioxide. This carbon dioxide is again getting in contact with carbon and it is getting converted to CO. This we have seen. So this is actually happening in the combustion zone, which is very, very important. Okay. Apart from this, inside the blast furnace, there is another very, very important zone, which we call the dead man's zone. Dead man's zone. What is this dead man's zone? The coke here in the dead man's zone, I'll show you also what happens in the dead man's zone. Basically, the coke here does not take part in the reaction. Okay. The coke in the dead man's zone, the coke in the dead man's zone does not take part in reaction. So the coke here will not take part in reaction themselves. But why then this zone is important? You can now ask that, okay, if the coke is not taking part into the reaction, then why this zone is important? Because this coke in the dead zone, it basically supports the entire charge materials and the overburden. Okay, so it supports the charge materials. So that is why this Deadman zone is so important. Now, let us see. how this Deadman zone is actually inside the blast furnace. Now, if this is my blast furnace, just please pardon my drawing. Uh, is not symmetric. I can understand that. But okay, shape is intact. So important is the shape. The shape of the blast furnace should be correct. So, okay, this is the belly part. You can understand that. And this is the hearth part. This is the Bosch area. This is the stack. Everything that we have discussed like that. Okay. Now, the Deadman zone, it is the coke in the Deadman zone. It is going to be something like this. So, it is a stagnant portion. Stagnant coke portion. Stagnant means whatever coke you have charged, a part of it is going to be like this. Okay. A part of it is going to be like this. Now, this coke that is there, now suppose this coke that is there, this is a coke, these are all the cokes. This coke will not take part into this reaction, into the reaction, reduction reaction. They will not take part in the reduction reaction. But though they will not take part in the reduction reaction, they are very, very important. Why they are important? Because they are supporting the weight of the overlying burden. Whatever burden, see, this is a huge weight. A lot of, you can say, the ore materials and along with the ore materials, the flux in the form of limestone, and these are all we are actually charging, right? We are actually charging. So the burden material is huge actually. Okay. So that the weight of the burden material, okay, needs to be supported. The weight of the burden material needs to be supported. Because if that is not supported, then everything is in vain. राइट सब कुछ बर्बाद हो जाएगा अगर हम लोग बार्डन मटेरियल को ठीक से सपोर्ट नहीं कर पाए तो वो बहुत ही जरूरी है और वही करता है द डेडमैन जोन एग्जैक्टली दैट इज बीइंग डन बाय द डेडमैन जोन राइट सो नाउ आई थिंक द आइडिया इज क्लियर व्हाई इट इज इन टर्न राइट नाउ we will talk about one very important concept, right? And that concept is basically how we charge the materials. How we charge the materials. Suppose this is a blast furnace. This is the throat portion. This is the stack. Yep. Just a minute. So please draw this. And now we will discuss something very important. I want all of you to draw. Okay. This is the blast furnace. Please draw. Take some time and draw. We'll have Okay, now let us continue. So I think you have drawn this portion. Okay. Now, how we charge it? How we charge the materials? Now we charge the materials layer by layer. Now, like this is very important. We charge the materials layer by layer, something like this. Okay. See, so how we will charge the materials layer by layer? It is like the first layer is going to be coke. The first layer is going to be coke, followed by ore. Then again, there is going to be the coke layer. Then again ore. Then again coke, something like this. So it is coke, ore, coke, ore, coke, ore, like that. Similarly, in this side also. So it is coke, followed by ore. Then it is coke, followed by ore. Then it is again coke, followed by ore. So these are the black are the shaded are the coke region, and these are the ore region. Okay, like this. Now, the descending ore layers are separated by permeable layers of coke, and gas passes through these ore layers. Okay, so what is happening is you understand one thing, that what is the main purpose of giving such layers? Why we will when we will charge, why the charge should be layered, like coke layer followed by gold layer, then coke layer followed by gold layer. You see, inside the blast furnace, most of the reactions that are taking place in the blast furnace, always remember, they are basically gas solid reactions. So most of the reactions that are taking place inside the blast furnace, they are gas solid reactions. Okay. Now, as most of the reactions are gas solid reactions, gas solid reduction reactions. So these gases, they will have to, these gases are only reducing. Okay. These gases are only reducing the, I can say the ore or the charge materials. But as the gases are reducing the ore or the charged materials, the reducing power of these gases has to be high. The reducing power of these gases has to be high. But now suppose there is a gas which is generated here. Now this gas has reduced the ore layer. This is the ore layer. The gas has already reduced the ore. Okay, so reduce the ore means, suppose let us take an example, Fe2O3 has got reduced to FeO. Okay, like that. It has reduced. Fe2O3 has got reduced to Fe3O4. Fe3O4 has got reduced to Fe. Now, in the process, as the gas has already done that work, that reduction work, so now the reducing power of the gas has decreased. Now the reducing power of the gas has decreased quite a bit, right? Now, when this gas will again, when this gas will again come in contact with this coke, then what will happen? When this gas again comes in contact with the coke, the reducing power increases, because as the gas is coming in contact with the coke, it increases the reducing power. So now the reducing power of the gas increases. Now, as the reducing power of the gas increases, again now when the gas is coming in contact with the ore, it can reduce more. Okay, now it can reduce more. It has got more reducing power. But again, in the process of reducing the ore, some of its reducing power has decreased. So again, now when it comes in contact with the coke, its reducing power increases. Now again, it can reduce the ore more efficiently. After that, again, it needs to increase the reducing power. So you can now understand why we are charging it in layers, right? Now, this part is done. Now we will see the reactions in various zones in the blast furnace. Reactions in various zones in the blast furnace. So this is very important. First, we'll talk about reduction reactions in the upper zone. Okay. Upper zone means upper part of the blast furnace. We'll first see this. Reduction reaction in the upper zone. So what are the reduction reactions that take place in the upper part of the blast furnace? The first is Fe2O3 is coming in contact with CO gas, carbon monoxide gas, and it is being reduced to Fe3O4 plus CO. Okay. This is one reaction. Another reaction which is taking place is this Fe3O4. It will again come in contact with the CO gas and it will get reduced to FeO plus CO2, right? So these are the reduction reactions. Mainly these are the reduction reactions. Now let us understand. Now let us understand why the reaction is taking place like this. Sorry. So if we try to see one thing, like just see the blast furnace. So in the blast furnace, at the top part of the blast furnace, a lot of carbon monoxide gas is already present. Because why a lot of carbon monoxide gas? See, understanding the thermodynamics or this part is important. Why you see? Because that is why then you will understand why the reactions are taking place in such a sequence. Okay, you do not need to mark up all the things. We should understand why it is happening like that. So a lot of carbon monoxide gases are already present at the upper part of the blast furnace because a lot of reduction reactions have taken place. And another important thing is that I have told you earlier also that as the temperature is more, at high temperature, what happens? Our CO gas is more stable compared to the CO2 gas. At high temperature, CO gas is more stable compared to CO2 gas. Okay. So exactly. So what is happening here is that what is happening, the reduction reactions in the upper zone. So you see the charged materials that we are charging, it is mainly basically Fe2O3. Okay. Now this Fe2O3 is coming in contact with the CO gas because there are many CO gas, a lot of CO gas, and it is getting reduced to Fe3O4 plus CO, right? Again, the Fe3O4 is coming in contact with the CO gas and it is getting reduced to FeO plus CO. Okay. So this is basically, these are the main reactions that are taking place at the upper zone, at the upper part. Now, reaction in the middle part. If I talk about the reaction in the middle part, reaction in the middle part. This is also called the isothermal zone. Very important. So sometimes directly questions come like which zone is called the isothermal zone. So what is the mostly the reduction reaction that is taking place at the middle part of the blast furnace? It is FeO coming in contact with the CO gas, and it is basically giving us Fe plus CO2. So this FeO coming in contact with the CO gas, that is iron oxide Fe. This we actually call Ustate. This is what we call as Ustate. So FeO coming in contact with the CO gas, it is getting reduced to iron plus CO2. So this is the reduction reaction which is made basically taking place in the middle part of the blast furnace. So this reaction we call indirect reduction of Fe. This is sometimes called as indirect reduction of Fe. Indirect reduction of Fe, right? And there is another reaction. There is another reaction which we call water gas shift reaction. Water gas shift reaction. Right? So this reaction is, what is this reaction? The water, high water stream, when it comes in contact with the high temperature water stream, when it comes in contact with the CO gas, carbon monoxide gas, it is going to get converted to H2 plus CO2. Okay. So that means this is also, this is how basically CO2 is produced inside the blast furnace. This we call water gas shift reaction. So mainly these are the reactions which take place at the you see the upper and the middle part of the blast furnace. So all you need to remember is that at the upper part of the blast furnace stack region, what is happening? Fe2O3 is getting reduced to Fe3O4 and Fe3O4 is getting reduced to Fe. This is basically in the upper part. Middle part में क्या हो रहा है? Middle part में mainly हो क्या रहा है कि FeO जो बना है, FeO is basically getting reduced to iron. Okay, so FeO is coming in contact with the CO gas and it is getting reduced to iron. That is what is happening in the middle part of the blast furnace. Or water gas shift reaction is also taking place in the middle part of the blast. Another thing, okay, so these are the reactions. Now we will talk about the reaction in lower zone. Reaction in lower zone. Reaction in lower zone in the blast furnace. So when I talk about the reaction in the lower zone, So it is FeO plus carbon. Now see, lower zone में अभी बचा क्या है? Like you just understand it like that. Already Fe3O4 has got reduced to already Fe2O3 has got reduced to Fe3O4. Okay, Fe3O4 has got reduced to FeO. अब क्या बचा है? अब रिड्यूस होने के लिए बस FeO ही बचा है. So lower zone में क्या होगा? Lower zone में mainly FeO will get reduced. So FeO plus carbon, it is getting reduced to iron plus CO, right? It is getting reduced to iron plus CO. So this is called direct reduction. Why I call it direct reduction? Direct reduction of FeO. Why we call it direct reduction of FeO? Because you see, FeO is coming in contact with the carbon directly and it is getting reduced to iron plus C, right? Actually, reaction does not take place like this. Actually, reaction does not take place like this. The reaction that I have written here, it is a combination of two reactions. So I can say this reaction 1, just remember this, reaction 1 is a combination of two reactions. So one is FeO plus CO, it is getting converted to Fe plus CO2. Okay. Another is, so FeO, it is coming in contact with the CO gas and it is getting converted to Fe plus CO2. Okay. This is one. Another is this CO2 is generated. Now this, because the temperature is high, अब क्या होगा? Because of the high temperature, the CO2 will come in contact with the coke and it will form CO. Because we know that at high temperature, what happens? At high temperature, our CO is more stable compared to our basically CO2 at high temperature. So CO2 will come in contact with the carbon and it is going to give you 2 times of CO, right? So exactly this happens. So these two reactions that we have written here, this is called the a very important. This both these reactions are very important, and this what we call the raceway combustion reaction. Raceway combustion, raceway combustion reactions. Raceway combustion. Okay. Always remember this. Now you can actually type if you have any one of you who are actually watching live. So if you have any question, I will just ask you, please type it in the chat box. Please type it. Do you have anything to ask? Or everything is like whatever we are discussing, you are understanding? That is the main purpose of the discussion. What? Now, let us move forward. Mm, So raceway combustion reaction we have done. Now, direct reduction of oxides. We'll be talking about the, see, now when these oxides are there, different oxides are there, like when we talk about P2O5, when we talk about SiO2, they are all the gangue materials, right? So these gangue materials will also get reduced. These gangue materials will also get reduced, okay, when they will come in contact with the coke. So let us understand how. Direct reduction of oxides in gangue Like, so what are the gangue materials mainly? We have P2O5, we have MNO, and we have SiO2, etc. Things like that. So P2O5, if I'm talking about P2O5, it will come in contact with the carbon and it is getting converted to phosphorus plus 5 times of Cu. This is what is happening, right? Similarly, SiO2 is coming in contact with the carbon. Okay, it is becoming silicon plus 2 times of Ca, right? And MnO, manganese oxide, coming in contact with carbon. Okay, it is getting reduced to Mn plus Cu, right? This is all right. But there is one thing, all these will get reduced like this. But there is one gangue material which will not get reduced like this, and which is actually very problematic. It will create a lot of problem. Which is that material? Which is basically sulfur. Sulfur is the element which creates a lot of problem. And even in the after the iron making process, when you will study the steel making process also, there also you will see that sulfur inclusion is really very problematic. And it is very difficult to remove the sulfur in the steel making process. So whatever the idea is, uh, maximum sulfur should be reduced in the iron making process itself. Because why? Because see, steel making is oxidizing condition. In the steel, iron making is the reducing condition. Like everything, all the reactions that we are discussing, the reactions are basically reducing reactions. All the reactions that we are discussing, these are reducing. So the atmosphere is reducing. So whatever sulfur you need, you can extract the sulfur, or means the sulfur can be reduced in the reducing condition, but oxidizing condition, sulfur removal becomes more difficult. Okay. So the idea should be that maximum sulfur should be removed in the steel making process. But again, sulfur directly you cannot reduce it like this. So what we need is, for removal of sulfur, we need to add lime, CaO. And when sulfur is there already and it is coming in contact with the carbon, so what happens? This CaO, it is going to catch the sulfur. So it is going to become calcium sulfide, CaS, and it will form carbon monoxide. So CaO has trapped the sulfur, yeah, and it has become calcium sulfide, right? So that is why addition of lime is very, very important, because if you are not adding lime, your sulfur is not getting removed. Okay. So that was the main idea of the sulfur. And now we will basically discuss about, about the reactions in more details. The reactions that we saw here, uh, we will discuss about these reactions. The reactions that we talked about, we'll discuss more about those reactions now. So direct reduction and indirect reduction. Direct and indirect reduction. If I talk. Okay. So carbon. So if I am talking about the direct reduction, if we focus on direct reduction, right? So I can say that FeO solid, it is coming in contact with the carbon solid. Direct reduction means directly it is coming in contact with the carbon. That we call as direct reduction. So FeO is coming in contact with carbon directly, and it is giving us Fe plus CO gas. Right? So I can say from here 1 mole of carbon can take 1 mole of iron. Right? From here it is clear that 1 mole of carbon is taking 1 mole of iron. Right? But actually, my reaction is not taking place like this. How is my reaction taking place? My reaction actually is taking place like this. The FeO solid is coming in contact with the CO gas, and it is becoming Fe plus CO2. Right? Fe solid plus CO2 gas. This is what we are getting. And this CO2 gas is basically coming in contact with the carbon. Okay. And it is becoming CO at high temperature. So this is also gas and this is also gas. So these two, this is a combination of these two reactions. You need to understand. The direct reduction reaction that I have written, where I have just written FeO coming in contact with the coke, is getting reduced into iron and CO gas. The reaction is not taking place like this. Rather, the reaction is taking place in this way, that FeO is coming in contact with the CO gas. It is reduced to iron and CO2. Now, this CO2 gas is basically coming in contact with the carbon, and it is, after coming in contact with carbon, it is basically giving us 2 times of CO. Right? So this is called basically carbon gasification reaction. This reaction, CO plus carbon giving us 2 times of CO. This reaction is what we call carbon gasification reaction. So always remember, they can directly ask you which reaction is basically carbon gasification reaction. So if they ask you, then you need to understand and you need to know that which reaction is carbon gasification reaction. Okay. So, okay, Arnav is asking, can you please explain the factor affecting blast furnace? Yes, we will discuss the factor affecting blast furnace. No problem. Let's see. Sequentially, we will move to that portion. So please watch the entire the class, and you will get to know. So, like I was discussing, CO gas plus carbon is giving us 2 times of CO. CO2 gas plus carbon is giving us 2 times of CO. So this is called the carbon gasification reaction, and this carbon gasification reaction basically takes place. This carbon gasification reaction takes place at a high temperature. Okay, so at the high temperature only, we have seen that the stability of CO or the carbon monoxide gas is more. Stability, so it is more at the high temperature. Okay. Now, uh, indirect reduction reaction. We'll be talking about the indirect reduction reaction now. Okay. Now, most of the indirect reduction reaction, you must understand that most of the indirect reduction reaction takes place at the upper part of the blast furnace. Because at the upper, indirect means what? Indirect means that they are not coming in direct contact with the coke. Okay. So at the upper part of the blast furnace, mostly what are there at the upper part of the blast furnace? At the upper part of the blast furnace, you will find the gases. CO gas is there and CO2 gas is there mostly at the upper part of the blast furnace. Okay. So you have the indirect reduction reaction. So let us write the indirect reduction reaction that are taking place at the upper part of the blast furnace. So Fe2O3 plus CO, it is getting converted to Fe3O4 plus CO2 gas. Okay. So this is one. And another is Fe3O4 plus 1.25 CO. It is getting converted to 3 times of FeO solid plus CO gas plus CO2 gas. Okay. And another is FeO solid. It is getting converted to, FeO solid coming in contact with CO gas. Right. So these are all my indirect reduction reactions. I have just balanced them. Nothing. Now in the upper, up in the blast furnace where temperature is less than 900 degrees Celsius, in situ CO generation by carbon gasification is not possible. So what happens? Ore reduction is sustained by CO generated at the lower part of the blast furnace. So what I mean to say is that you see at the upper part of the blast furnace, the temperature is not high. Okay, if I'm talking about the upper region of the blast furnace, the temperature is not high, not that much high. Okay, so as the temperature is not that much high at the upper region of the blast furnace, so what happens there is that the carbon gasification reaction that we talked about. What reaction is carbon gasification reaction? CO2 coming in contact with carbon is producing CO. This reaction is called the carbon gasification reaction. So this reaction will only take place when the temperature is greater than 900 degrees Celsius. This reaction will only take place when the temperature is greater than 900 degrees Celsius. If the temperature is less than 900 degrees Celsius, that reaction will not take place like this. Okay. So the CO is less. CO is less there. So you do not have much CO gas. Okay. So most of the reduction reaction will then by the CO will actually take place at the lower part of the blast furnace. Okay. Now if I talk about direct reduction. Now, if I talk about the direct reduction is basically endothermic. Direct reduction Okay, so direct reduction is basically endothermic. Direct reduction is endothermic. It takes place at the lower part of the blast furnace. It takes place at the lower part of the blast furnace. Why? First and foremost, we need to understand why the direct reduction is taking place at the lower part of the blast furnace. The direct reduction is taking place at the lower part of the blast furnace because at the lower part only the coke is present. So your ore can directly come in contact with the coke at the lower part of the blast furnace only, right? So direct reduction is taken, and direct reduction, always remember, it is endothermic. Okay. So as it is endothermic, so I can also say as direct reduction is endothermic, so high temperature is required. For direct reduction, high temperature is required. So this is another reason why the direct reduction reaction is taking place at the lower part of the blast furnace, because only at the lower part of the blast furnace the temperature can be high. So your temperature should be greater than 900 degrees Celsius. And this temperature is only at the lower part of the blast furnace. And another thing, just like the direct reduction reactions are endothermic, okay, just like that, the indirect reduction reactions are exothermic. Always remember, direct question comes. Indirect reduction reactions in the blast furnace, they are exothermic. They are basically exothermic. Okay. So directly question comes like direct reductions in the blast furnace are endothermic or exothermic, ऐसा करके question दिया जाता है direct. So always remember, indirect reduction reactions are exothermic and direct reduction reactions are endothermic. And indirect reduction reactions will take place at the upper part of the blast furnace, right? But one thing is, now if I ask you one thing, which reaction is better? Means better means from the economical behavior. Okay, which reaction is basically from the economical point of view, which reaction is more economical? Direct reduction reaction or okay, just we'll resume back in 5 minutes. Just we'll resume. Just stay everyone. Okay, we'll resume back in 5 minutes. Okay, so let us resume back. Thank you. Yeah, so I was asking like which is more economical? Now, more economical means why I ask this question, you need to understand that what is meant by this. If I talk about the direct reduction reaction, if I talk about direct reduction reaction, if I talk about direct reduction reaction, okay, if I talk about direct reduction reaction, then in direct reduction reaction, 1 gram mole of carbon can reduce 1 gram mole of Fu. One gram mole of Fu. So 1 gram mole of carbon, okay, can reduce 1 gram mole of Fu. See how I can say this? Because what is my direct reduction reaction? My direct reduction reaction is basically this. FeO solid, it is basically coming in contact with the carbon, giving us iron solid plus CO gas. Okay, this is exactly what we are getting. So 1 gram mole of carbon can reduce 1 gram mole of Fe. But if I talk about indirect reduction reaction, in indirect reduction reaction, what is happening? 1 gram mole of oxygen of Fu, we need 3.3 gram mole of CO. So if I'm talking about indirect reduction reaction, if I'm talking about indirect reduction reaction, then try to understand what is happening. So if we talk about indirect reduction reaction, I take an example like 3 times of Fe2O3. Okay, it is coming in contact with CO and we are getting Fe3O4. Okay, Fe3O4 means 2 times of Fe3O4 plus CO gas. Okay, now here if you see, here what is happening? One, and if you look at this also, okay, so this reaction, okay, we will not talk about this reaction now. Let us focus on this reaction, which is basically FeO. FeO solid, this is type. It is coming in contact with 3.3 CO gas, gram moles of CO gas. And why I took this reaction? Because directly this is the step from where you are getting iron. So I want to reach the final product, which is my iron. Okay. So that is why we are considering this. Here you can see that what is happening here. Uh, Here basically to remove 1 gram of oxygen, to remove 1 gram mole of oxygen from FeO, how much CO is involved? 3.3. But here just one to remove the 1 gram mole of oxygen from the FeO, 1 gram mole of carbon was enough. But here 3.3 gram mole of carbon is required to remove 1 gram mole of oxygen. So here you need more fuel. I can say more carbon means what? More fuel is required. So indirect reduction reaction needs more fuel. Okay. Or conversely, I can say is less economical. Conversely, I can say it is less economical. So y-axis is del G formation, delta G of formation. Okay. So it is not delta G not actually, it is delta G of formation. Means we are actually looking at, see, delta G not means what? Means that means we have to actually say that it is like equilibrium. Okay, equilibrium condition. But here we are, what we are doing in the Ellingham diagram. In the Ellingham diagram, what we are doing is we are, means along the x-axis, we are increasing the temperature or decreasing the temperature likewise. So it will be more good to say that it is going to be the del G formation, delta G formation for the metal oxides. Okay. Uh, so is it now okay? Okay. Now you see, now we can basically say that indirect reduction reactions. So in the note, now what we can write is that direct reduction reaction is more economical compared to indirect reduction reaction. Now you know the reason. Okay, right. Now we will see uh, now some of the important things, like we'll discuss very important things now, which is called the kinetics of gas solid reaction. Kinetics of gas solid reaction. I think your doubt I have actually cleared, right? Kidimani, I'm asking you, you have actually asked this doubt. Okay, good. So this is the kinetics of gas solid reaction that we'll be talking about. Now, while talking about the kinetics of gas solid reaction, what are the concepts that we are going to cover? First, we will discuss the concepts to be covered in this section. What are the concepts that we will cover? The concepts that we will cover is, we will talk about the mechanism of iron oxide reduction, mechanism of iron oxide reduction, mechanism of iron oxide reduction, followed by kinetic steps and shrinking core model. We'll talk about kinetic steps and what is called shrinking core model. This is a model we'll talk about, shrinking core model. And then we will see kinetics for chemical control process and gas film control process. Okay. So these are some of the things we will see, right? Okay. Now let us see models for gas solid reaction. Models for gas solid reaction. There are basically two types of models. If I talk about the models for gas solid reaction, there are two types of models. So what are these two types of models? One is called progressive reaction model. Okay. And another is called, one is progressive reaction model, and another we will call basically no. So first we will be talking about the progressive reaction model. So what is this progressive reaction model? What is this progressive reaction model? So this model assumes that the gas reacts uniformly throughout the entire volume of the solid. What it means? Suppose this is my ore. Suppose this is my ore, okay, which is a solid. Now, this model, progressive reaction model, this model assumes that, what is the assumption of this model? This model assumes that throughout the solid, hmm, in each and every part of the solid, my gas is reacting in the same manner. My gas is reacting in the same manner in each and every part of the solid. Okay. That means, see, ultimately, you need to understand one thing, that there are gases all around. Like inside the blast furnace, gases are there all around this solid particles. But inside these solid particles, gases are not there. Inside these solid particles, gases are not there. So gases, while the gases will react, how will the gas react? The gas will first react with the boundary. Okay, and from the boundary only the reaction will proceed inwards. But progressive reaction model is not like that. This model assumes that the gas interacts uniformly throughout the entire volume of the solid. Okay, not just at the surface. The reaction progresses gradually and uniformly from outside to inside. Okay, and what are the key features of the progressive reaction models? The key features are, okay, the key features are, first, the reaction occurs throughout the solid. Throughout the solid. This is number one. So as soon as the gas reaches any interior point, reaction begins there. So this progressive reaction model is saying that there is no time lag between the reaction and you see between the reaction and the gas reaching there. So as soon as the gas is reaching, okay, the reaction starts. So this is one thing. And Your doubt is being cleared. I don't know why are you repeatedly asking the same. Okay. And this is one, the reaction occurs throughout the solid. And second is no sharp reaction bounded. There is basically no sharp reaction bounded. No sharp reaction boundary is there. So unlike the shrinking core model, which has unreacted core, in case of shrinking core model, they have unreacted core plus product layer, but progressive reaction model, in the progressive reaction model, they do not have any distinct boundary. So we have two models. One is what one we call the shrinking core model. Okay, one we call the shrinking core model. Another we call what the progressive reaction. So shrinking core model basically it says that the core is going to shrink. Why the core is going to shrink? I tell you now. Suppose this is basically my this was my uh, suppose this is my Fe3, Fe2O3. Okay, this is my Fe2O3. So the Fe2O3 first it is going to come in contact with the carbon or the gas. The reducing gases will not in carbon. Okay, the reducing gases will first come in contact, and this is going to affect the surface of the Fe2O3. So the surface of the Fe2O3 will get reduced to Fe3O4. Subsequently, Fe 304 is getting reduced to FeO, and subsequently FeO is getting reduced to iron Fe. So the shrinking core model says that Fe2O3 जो surface में है वो पहले reduce होगा और वो reduce होके Fe3O4 हो जाएगा. उसके बाद the reduction reaction start from the surface only because the gases are directly coming in contact with the surface only. So the ultimately Fe2O3 जो है जो पहले मेरा Fe2O3 था that is going to shrink in size and get concentrated at the core. So this is basically my shrinking form, nothing more than that. Okay. So like I can give you one example from here. So kinetics of the iron oxide reduction, if you try to understand. So you see, यहाँ पे the Fe2O3 that is at the core. This is Fe2O3. This is Fe3O4. Fe3O4. Okay. And then there is a porous layer. This is the porous layer, which is nothing but FeO. There is a porous layer, and this part is basically our oostite, which is FO, oostite. Okay, so this is exactly how the reduction reaction happens. Okay. This is exactly how the reduction reaction happens. So we are discussing the actual mechanism of the reduction reaction, right? So this is the gas boundary film. This is the gas boundary film. So this is how the reaction progresses. Right. Now, now we talk about the blast furnace fuel. So this is something very important. We talk about the blast furnace fuel, which is the main fuel of the blast furnace is. What is the main fuel of the blast furnace? It is the coke. Coke is the main fuel of the blast furnace, right? So we'll talk about the blast furnace fuel. Main blast furnace fuel. Which is nothing but so previously charcoal was used mainly. Okay. In the blast furnace fuel, previously charcoal was used. Okay. But charcoal could not continue. Why we need to change the fuel then from charcoal? We had to move towards the coke. Why? Charcoal could not continue because why? What are the reasons? So can you please any one of you say that what can be the reason why charcoal could not be used? So charcoal could not continue because charcoal had low mechanical strength. So see, inside the blast furnace, when the reduction reactions are taking place, uh, not only means reduction reactions are obviously important, but apart from that, another thing is also very important. And what is it? That is to support the overlying burden. That is very important to support the overlying burden. So if the charcoal is having the low mechanical strength, if the charcoal is having low mechanical strength because what it is soft and brittle, then it cannot support the overlying burden, like we discussed it earlier also. Okay, so it easily crashes under the burden weight and it generates a large amount of fines. So after crushing the charcoal, see charcoal, if the lumps were like this, if the lumps were initially like this, now after crushing, it will become fine. Obviously, the lumps will become fine. And as the lumps will become fine, what will happen? Passing of gas through the fines, okay, will be difficult. So the reducing gases, they will not be able to pass so easily. Okay, so that is going to impact our overall reduction capacity. Okay, that is going to impact our overall reduction capacity. So that you need to understand. Okay, now, so which ultimately what happens is that it will choke the furnace. These fines will choke the furnace and it will reduce the ultimately reduce the permeability. Permeability means the ability of the gases to pass through this. And ultimately, all this will give rise to pressure drop. Delta P will increase. Delta P means the pressure drop. Pressure drop will increase basically. All this will give rise to increase in the pressure drop and disturb the gas flow and disturb the gas. So this is something which we need to understand, right? Now the best alternative is now available. What is the best alternative that we have now? The best alternative available is basically the coke, metallurgical coke. So metallurgical coke, basically how metallurgical coke is formed, like if we take the coal and if I in the presence of air or oxygen, if I heat it, you will get the coke. So coke, how it is more useful than the coal, because coke has got certain things like coke. It is basically, it is a volatile matter. In the coke, the volatile matter is removed. Now if I am using coal, suppose if you are using coal, then a lot of volatile matters are there. Volatile matters means, so say for example, I can give you one example, which is the water content. So coal is having a good amount of water content. Now when you heat the coal, then this water content is going to vaporize and it will take some temperature. The heat that you are, the temperature that you are providing, substantial amount of temperature will be taken by these volatile materials. Okay, so ultimately you need to heat them more. Hmm. But this problem is not there if you are using coke, because coke is having less volatility, right? So you can say advantage of coke, coke is having less volatile matter, right? And coke is also, in the coke, they are more mechanically strong. So you can say coke is more mechanically strong compared to the coal. Okay, so it can basically, what will happen if it is more mechanically strong? It means that it can support the overlying burden more easily. It can support the overlying burden more easily, right? So this is it. So now we will basically talk about the functions of the coke. We will talk about the functions of the. So it is the fuel providing the heat for meeting the endothermic requirements of the chemical reactions. First function is obviously, you can understand that it is the fuel, it is the main fuel, okay, which provides heat, which provides heat for meeting the endothermic requirements of the chemical reactions. Endothermic requirements of the chemical reaction. Okay, and melting of slag and metal. So this is being done. So it is the main fuel. It produces and regenerates reducing gases for the reduction of the iron oxides. So obviously the reducing gases are being produced by the coke only, right? So it produces and regenerates reducing gases. like CO2, CO, and H2. Okay. Now, it provides an open permeable bed to which the slag and the metal pass down into the hearth. This point is something very, very important. So coke is having good permeability. So if these are the lumps of the coke, they will allow the gases to pass through them, number one. And also, because the cokes are permeable, so the hot metals can also pass through these cokes, hot metal as well as the slags. Okay, so hot metal and slag, they can also pass easily through the coke because the coke is permeable. So you can write this point like it provides an open permeable bed. Permeable bed. Okay, through which slag and metal pass down. Slag and metal pass down. Right? So this is exactly what happens. And now other things are also there, like it carbonizes iron, thereby lowering the melting point and subsequently the working temperature of the blast furnace. This is also very important. So coke, what it does, from the coke only, okay, the carbon is basically getting added into the iron. Okay. So what happens if you look at the iron carbon phase diagram? I think that all of you are familiar with the iron carbon phase diagram. So if you look at the iron carbon phase diagram, what happens? Pure iron, the melting point is higher, is above 1500 degrees Celsius or 1550 or something like that. Pure iron. Now, when you subsequently add carbon in iron, then what happens? The melting point decreases, right? So, this is exactly what this coke is also doing. So, you can write it carbonizes iron. Carbonizes iron. Carbonizes means it adds carbon with iron. It carbonizes iron, thereby lowering its melting point. Thereby lowering its melting point. Okay. So, and obviously, if the melting point is lowered, what is going to happen? Obviously, less temperature is now required. Okay. Now, in the modern furnaces, with the injection of auxiliary fluid fuels, achieving coke rate as low as 400 to 500 gram per ton of hot metal is achieved. So this much we can basically achieve because now in modern furnaces we are also using many fluid fuels and they are basically injected from the lower side of the furnace. Okay, so this is one thing. Now we need to understand what are the quality requirements of the coke. This is something important. Quality requirements of coke. Quality requirements of coke. What are the quality requirements of? One is the efficiency of the blast furnace. It directly depend on the permeability of the charge in the furnace, and which in turn is directly dependent upon the quality of the coke. So the coke has to be very, very permeable. So coke has to be permeable. Why? Because if the coke is not permeable, then what will happen? The reducing gases will not pass through the coke. The reducing gases will not pass through the coke easily. Okay. And if the reducing gases are not passing through the coke, then obviously there is going to be insufficient reduction reaction. Okay. So this is one. So this is one of the important thing, which is the permeability. The chemical composition is also important. The chemical composition is determined in terms of contents of fixed carbon as sulfur, phosphorus, and other deleterious impurities. So what happens is that if the coke is basically having higher ash content, then that coke is not desirable. Why? Higher ash content means the available carbon of the coke decreases. If the ash content of the coke is more, so that means carbon content is less. Okay, that means the carbon content is less. Now, if the carbon content is less, then you can understand one thing, that what is going to happen. Definitely, improper reduction is going to happen and the coke is not of much good quality. Okay. And ash usually contains refractory oxides also. So ash content is higher means there are higher of these things like SiO2, CaO, Al2O3. Okay, these are the refractory oxides. And what will happen? Because see, sulfur, if sulfur is present in the ash, now that sulfur is going to create problem because that sulfur will seep into the hot metal. So that is one problem that we will face. And another thing which along with sulfur is the phosphorus. So phosphorus are also usually present in the ash in the form of inorganic compounds. So high ash content is never good. Okay. And if the ash content is high and inside that ash, if the sulfur content is high, then you need to add more flux. Okay. Second is about the reactivity. When we talk about the reactivity means the reactivity of the coke I am talking about. The rate at which the carbon atoms of the coke reacts with the oxidizing gases. Okay. It reacts with oxidizing gases. Like oxygen, CO2, H2O, etc. This is reactive. There is another very important thing which is called the coke reactivity index, CRI. CRI stands for coke reactivity index. Coke reactivity index. Now, how easily coke reacts with carbon dioxide gas at high temperature? This is basically determined by the CRI, coke reactivity index. So, coke reactivity index tells us how easily coke reacts with carbon dioxide gas with CO2 gas at high temperature. So this is determined by the CRI. Now, inside the blast furnace, what happens is we need to understand why CRI is important. Why is it important? Because inside the blast furnace, the raceway and lower stack CO2 reacts with coke. So, inside the blast furnace, if I'm talking about, then the temperature is quite high. And at the hearth region, or just above the hearth region, what is happening is there is the raceway. Okay, so raceway means the temperature is quite high inside the blast furnace. Um, and the CO2, it directly comes in contact with the coke. So this is the carbon of the coke coming directly in contact with CO2 gas. Okay, and it is basically giving us this carbon plus CO2 gas. Okay, giving us 2 times of CO gas. Right? Now, if the CRI is too high, that is if the coke reacts too fast, then also it is not good. And if we will see that if the CRI is too less, then also it is not. First and foremost, let us see that what will happen if the CRI is too less. If the CRI or the coke reactivity index is too less means is too low, then what is going to happen? If the CRI or the coke reactivity index is too low, what will happen? If it is too low, then there is going to be incomplete reduction reaction. So incomplete reaction means coke coming in contact with CO2 gas, giving us 2 times of CO. This takes place at a temperature greater than 900 degrees Celsius minimum. Always remember this. But if the CRI of the coke is less, then enough CO2 will not be produced. Okay? Enough CO2 will not be produced because this reaction itself will not take place that much if the coke is not reacted. But now let us see if the CRI coke reactivity index is too high, then what is going to happen? A lot of reaction will take place. It will react very fast, number one, and it weakens the structure. Because of excessive reaction, the coke का जो अपना जो structure है, the structure of the coke, it is going to get weakened because the coke will become more porous. Okay, so it weaken the structure. It weakens the structure. Then break into fines. So the coke, it is broken into fines. It breaks into fines. Okay, cause pressure drop. Why it causes pressure drop? I tell you. Very, very important concept. So basically, our delta P increases, pressure drop increases. Suppose, see, this is a blast furnace. Just rough diagram. Suppose this is the blast furnace. Okay. Now, what is happening if the CRI or the coke reactivity index is too high? Then what is happening? You see, the structure is weakened and the coke is breaking into fines. And as the coke is breaking into fines, so suppose these are the coke fines. The coke is broken into fines like this. Now, the permeability of the material has decreased. So, as the permeability of the material has decreased, many of the gases, reducing gases, they will not be able to go up through the pores because now they are fines. Okay, so it will not be able to go out. So ultimately, there is more pressure here, more pressure because more reducing gases at the lower part of the blast furnace. and there is less pressure here, because low pressure, because these gases cannot pass easily. So your pressure drop del P will increase. So that is why they are saying that it causes pressure drop. Okay, causes channeling also. Now, what is channeling? Causes channeling. Channeling means what? Channeling means channeling means that suppose we have the coke. Okay. Now that portion, those parts where the permeability is less, from those parts the gases cannot move. Then the gases will try to move from only those parts the where they will get the right path, where they will get the right path to move. Okay, from that portion only the gases will be able to pass. So this is called basically channeling. Okay, and ultimately it lowers the permeability and reduces the furnace efficiency. So you can understand one thing, like CRI should be optimum. CRI should be optimum. It should not be too high, because too high होने से क्या होता है, just now we have discussed, and it also should not be too low. Okay. Now, apart from CRI, there is another thing which we call the CSR, which is coke strength after reaction. Coke strength after reaction. Now, what is this CSR, or the coke strength after reaction? Okay. Coke strength after reaction means how strong the coke remains, how strong the coke is, or the coke remains after reacting with CO2. So after the coke has reacted with CO2, how much strength it can maintain. How strong the coke remains after reacting with CO2. So this is basically the coke strength after reaction, or the CSR. And blast furnace needs basically strong coke to maintain permeability and load support, right? So blast furnace, we should always remember, blast furnace needs strong coke. Because apart from the reduction reactions, another very important thing which is required or which is expected from the coke is that they will support the material. Okay. Now we talk about the relation between CRI and CSR, that is coke reactivity index and coke strength after reaction. Relation between coke reactivity index, which is the CRI, and CSR, coke strength after reaction. So what is the relation between them? If coke has high CRI, that is the coke reactivity index, that means it reacts fast. So reacts fast means what will happen? Its structure will weaken fast. Like we have seen that. Just now we discussed that what will happen if the CRI is more. What will happen if the CRI is more? So if the CRI is more, or if the CRI is too high, it weakens the structure. The structure is basically getting weakened. It weakens the structure, it breaks into fines. So all these are the problems which we will face if our CRI is more, coke reactivity index is. So blast furnace needs strong coke. Okay. And But if the CRI is more, then what is going to happen? If coke has more CRI, coke reactivity index, if it is more, then it reacts fast. It reacts fast, weakens the structure, weakens the structure, and ultimately, what happens? The coke strength after reaction decreases. CSR decreases. Okay. So the thing is, it is something like this that if the CRI is increasing, there is a trend which decreases the CSR automatically. So CRI increases, CSR decreases. But you see, both are important. But this is the challenge, right? If you increase or improve the CRI, coke reactivity index, your CSR, that is the coke strength after reaction, will decrease. So how to balance it? Okay. So, and what is an ideal coke? Which kind of coke? We will basically say that this is the ideal. An ideal coke should have low CRI value, coke reactivity index, it should be low, 20 to 25%. And it should have high CSR, coke strength after reaction. So you see, which kind of coke we are saying ideal? We are putting more importance on the coke strength. This is something important to understand. We are putting more importance on the coke strength after reaction. Okay, so that is 60 to 70%. More than the reactivity, we are putting important on the coke strength because in the blast furnace, what is expected from coke is it will just balance or it will take the underlying load of the burden. And apart from that, it will also not break down. Because if the coke itself breaks down into fines, what will happen? The permeability will decrease. Okay. Now size. Size of coke is also something very important. Now, size, why it is important? Because the size, it controls the permeability. It controls the size, it controls the permeability of the burden. Permeability of the burden. Okay. So the size, it basically controls the permeability of the burden, right? Now, if coke size is too small, now let us see. If coke size is too small, if coke size is too small, gaps between the particles blocks and the poor gas flow. So what happens? The gaps are blocked. The gaps between the particles, they are basically blocked. Okay. And poor gas flow, there is going to be, because see, permeability is reduced. So it will have poor gas flow. So ultimately, this will increase the pressure difference, and there is going to be problems like hanging and channeling. So see how questions will come. Generally, how questions are coming. Like they will just talk about hanging and channeling. And you need to understand that why this problem, hanging and channeling problem, comes into, or why this problem is there, why it comes into. That we need to understand. Okay. So if coke is, like we have said this, that if it is too large, what is going to happen? Now ensures decent stability of the burden. The coke must also ensure that the burden that we are actually charging, okay, they are coming with decent stability. Okay, so it ensures the stable descent of the burden. Right size maintains mechanical strength during descent. So you can say ensures stable descent of the burden. Ensures stable descent of the burden. Right size maintains mechanical strength during the descent and affects the reaction rates also. Reduction reactions occur. So how the reduction reactions occur? Reduction reactions occur at coke gas interface. Let us understand. So smaller size means higher surface area and more reduction reaction. So see, most of the reduction reactions, they are basically taking place, occur at coke gas interface. Okay. So if the size is small, comparatively small, then what is happening? The surface area is increasing. So if the surface area is increasing, the reaction rate is increased. Okay. But there is a problem. If the size is too small, then it becomes fine. And when the coke is becoming fine, then permeability decreases. And then overall the reduction reaction decreases because the gases are unable to get into those portions only. So when if the gases are unable to get into those portions, what will happen? What will happen? If the gases they cannot reach the sites for reduction, then partial reduction or a substantial portion will not be reduced. Okay, so exactly this is what happens. Now, the size factor we have seen. Now we will talk about the thermal stability of the coke. This is also very important. Thermal stability of coke. So let us see the thermal stability of coke. Just give me 2 minutes. We'll resume. Okay. Now we talk about the thermal stability of the coke. So thermal stability means its ability of the coke to maintain structural integrity when exposed to high temperature. So you can write it is nothing but ability of the coke to maintain its structural integrity. When exposed to high temperature. When exposed to high temperature. So that is, see, if the coke is not having thermal stability, what is the problem that we will face? If the coke is not having thermal stability, what is the problem that we will face? The main problem that we will face is like when it is not having thermal stability, that it will see inside the blast furnace, the temperature is very high inside the blast furnace. So if it is not having thermal stability, this is really going to be a problem. Okay. So a thermally stable coke, it will not crack, it does not crack, break, or disintegrate when it is heated for a long period of time. Right? So this is the thing. Right? Now, apart from that, the strength and abrasion resistance are also very important. Strength and abrasion resistance of the coke. Strength and abrasion resistance. Let us see what it is. So, why first and foremost, the strength you can understand, the strength of the coke that should be there. Now, abrasion resistance, why it should be there? Because you see, when we are charging the materials, including the coke in the blast furnace, so obviously the material is going to just come down with a, and there is going to be a lot of abrasion. Abrasion means there is going to be a lot of what should I say? There is going to be a lot of friction. Okay, there is going to be a lot of friction. Okay, with the blast furnace walls or things like that. So that is why. Okay, this abrasion resistance, the coke must be abrasion resistant. So there are certain tests like the tests that we actually do in order to see whether the coke is abrasion resistant or not. There are shatter tests. These are certain tests are there. I just write the names of the tests because getting detail of this test is not that important. So shatter test is there and tumbler test is also there. You can go through it. So these are the tests which test the abrasion resistance of the coke. And always remember that the coke we use in the blast furnace that must be abrasion resistant. Okay. And another thing is the blast furnace. What is as far as the quality of the coke is concerned? Okay, inside the blast furnace, as far as the quality of the coke is concerned, what is actually desired is that the coke reaction the coke reactivity index CRI that should be comparatively less, and the coke strength ratio, the coke strength after reaction, which is the CSR, that should be more. Okay, so that we have already discussed. Now we will talk about certain important things. Now we basically talk about the blast furnace products. Blast furnace products. What are the, when I talk about blast furnace products, what are the products of the blast furnace? What are the products of the blast furnace? When we say blast furnace products, the main products of the blast furnace are the main products of the blast furnace are the slag and the metal. Slag and metal. These are the main products of the blast furnace. Right? Now, blast furnace produces three different products. Three different products. What are they? It produces the gas, obviously, of gases. It produces the metal and it produces the slag. Okay, so these are the three main products. And in this chapter, quantity and quality of slag and metal generated and their utilization we will discuss. So slag is, what is slag? If I just I want to describe slag. What is slag? Slag is an unavoidable byproduct of iron making. Unavoidable byproduct of iron. So this is our slag. It is an unavoidable byproduct of iron making, and where basically the gangue materials will be there in the slag. The chemistry and volume of the slag depend mainly on the burden composition. The chemistry and volume of the slag, okay, depends on the burden composition. Okay. It depends upon not only on the burden composition, it also depends upon the hearth temperature. Hearth temperature is very, very important. It depends upon the hearth temperature. Okay. And it also depends upon the gangue constituents. Here, since the interest is in the molten products, more specifically the metal, whose chemistry is ultimately decided by the hearth temperature, is considered to be operating temperature of the furnace. So hearth temperature we consider as the operating temperature of the furnace. So I was talking about the slag. So slag is mainly made up of the oxides of, you can say, what are the compositions? Slag is mainly made up of the oxides of, so gangue from ore, gangue from ore, okay, like SiO2, Al2O3, Al2O3, okay, MnO, etc. And there are also fluxes. So the fluxes will also get into the slag only, like CaO, okay, MgO. These are the flux. And sometimes CaF2. Most commonly, we use CaO and MgO. Sometimes we also use CaF2. Co-cache is there. What are the co-cache? Means just now we discussed the ash of carbon. So in the co-cache, mainly you will get SiO2 and Al2O3. Other things can also be there. So slag means ultimately, in one word, I can say slag is nothing but it is gangue plus flux plus co-cache plus some reaction products. Some reaction products. Okay. Now we need to understand why slag forms. The basic idea. Why slag forms? Okay. So gangue plus flux will give you slag, right? For example, I tell you SiO. This is an acidic gangue. Okay. If I add CaO, which is basic flux, what is going to happen? CaO will fix this and it will become CaSiO3, which is a slag form, calcium silicate. So this is how you have actually trapped the SiO2, which is the acidic gangue, by adding CaO, which is basic flux. And in the slag phase, what is going? Which is calcium silicate, CaSiO3. Calcium silicate is going into the slag phase. Similarly, I can say that Al2O3, aluminium, plus if I add CaO, okay, which is a basic flux again. So calcium, aluminium, Al2O3, that is in the gangue form, right? Now basic flux we are using. What will happen? Calcium aluminates. You will get aluminates, calcium aluminates. Okay, which is in the slag form, right? Now we will basically understand the defosphorization. Defosphorization in basic slag. Very important step. Defosphorization in basic slag. Okay. Now let us see phosphorus in metal. when we are giving FeO in the slag, FeO is already there in the slag, and you are giving CaO because it is basic slag. CaO is going to be there. What you will get? You will get Ca4P2O9 plus 5 times of F. So that means now this phosphorus in the from the metal, it has got into the slag. Okay. So if you are having a basic slag, that is good for removal of phosphorus. Okay. So if your slag is having good amount of Ca, that is good for the removal of phosphorus from the metal. So I hope that you can now understand the utility of the slags. And that is the main idea. The utility of the slags. Right? Now, why slag is important? Now, we should talk about desulfurization. Dephosphorylation and desulfurization, these two are very important. Okay. Dephosphorylation and desulfurization. So always these two are very important. So for the desulfurization, what is the condition required? Desulfurization. The condition required is basic and reducing condition. So always remember, direct question comes. Condition required for desulfurization. What is the condition that is required for desulfurization? One is you need basic condition, and another is for desulfurization, you need reducing condition. So that is why you see our main motive is going to be, or our main target is going to be to remove as much sulfur as possible during the iron making process. Why? Because iron making is the reducing process. When you move to steel making, it is an oxidizing process. Now you see, can sulfur be reduced? Can sulfur be removed in the oxidizing condition? It is written clearly that basic slag is required and reducing condition is required. So desulfurization, you cannot do much of desulfurization during the steel making process because steel making is entirely an oxidizing process. So whatever sulfur we need to remove, we should be removing it during the iron making process. So let us see. Now, desulfurization. Okay. Now, we are having FeS in the metal. This is iron sulfide. Okay. Now, if we add CaO, this is basically basic slag, and we are giving carbon, what will happen? So carbon means reducing condition. So basic slag plus reducing condition. What is going to happen? CaS, calcium sulfide. This is going to go into the slag phase plus Cu. Right? So slag absorbs impurities. In one word, we can say that slag absorbs impurities like silicon, phosphorus, and sulfur from coke or ore or metal and holds them in the oxide and sulfides form. What I said, slag absorbs impurities right? Like silicon, phosphorus, and sulfur from ore, coke, or metal and holds them in the oxide or sulfide form. Now, slag chemistry, slag can be either acidic or basic. If I'm talking about the slag chemistry, so it can be either acidic or basic. So slag composition is usually expressed in terms of basicity ratio. So basicity ratio is very important in case of slags. And what is the basicity ratio in case of slag? We will see the basic oxides that are present in the slag. What are the basic oxides like CaO or MgO? These are the basic oxides. So we'll see, look for the basic oxides present in the slag, and we will also see the acidic oxides present in the slag. So it is the ratio between the basic oxides followed by the acidic oxides. So what are the acidic oxides? What are the acidic oxides? SiO2. SiO2 is acidic oxides. Al2O3. This is also acidic oxide. So basicity ratio is nothing but it is the ratio of the basic oxides to that of the acidic oxides. Now, if the ratio is greater than 1, what it means? It means that the basic oxides are more compared to acidic oxides. So, like there are more CaO and MgO in the slag, it tells us that. So, it is basically good for phosphorus and sulfur removal. Okay. And if there is more SiO2, then the slag is acidic. Then it is poor for refining, not suitable for blast furnace iron making condition today. So mostly in the blast furnace iron making, or mostly in the iron making process, we will be using the basic oxides only. Okay, not the acidic oxides. So you can basically write the basic slag. If the slag is basic, then what happens? It means high CaO, MgO, good for phosphorus and sulfur removal. It is good for phosphorus and sulfur removal, and it is preferred in modern blast furnace. Right. And acidic slag is not something which is good for the purification processes or the refining. Now, what decides the slag chemistry and volume? Obviously, one thing you can understand that if I am talking about that, what decides the slag chemistry and volume, you will say that Warden chemistry. Warden chemistry means whatever we are charging. Say, for example, if I tell that, okay, in the coke that we have charged, there is a lot of ash content in the coke, which is obviously not, but we cannot help it, suppose. So there is a lot of ash content. So ultimately, what will happen because of this ash content? Ultimately, the impurities, level of the impurities will increase. And most importantly, what will come from this ash content? Suppose if phosphorus and sulfur has come from this ash, then what kind of slag is required to remove them? Obviously, we will say the basic slag is required. One is reducing condition is required. Yes, reducing conditions we can give because we are adding coke. So carbon is already there. So reducing conditions. Now, apart from the reducing condition, you also need basic slag for their removal. So the point is that this depends. This basically depends on what we are charging, right? So, like gangue content in ore. So what decides slag chemistry and volume? Okay. One thing is Barden chemistry. It is decided by the Barden chemistry. How you have I have explained. Second, it is decided by basically co-cache. Obvious. If the co-cache contains, like if the coke contains 8 to 15% co-cache, which again contains SiO2, Al2O3, etc. Okay. These also go into the slag and increase the slag quantity. So ultimately they'll get into the slag and increase the slag quantity. Then obviously the slag chemistry is going to be determined by another thing, which I can say type and amount of flux added. Suppose if you have added CaO, then obviously the slag will be basic in nature. If you have added MgO, the slag is going to be basic in nature. On the other hand, if you have added Al2O3, the slag will be, or SiO2, the slag is going to be acidic in nature, right? So if you are adding limestone, dolomite, then the slag is basic in nature and more in volume, right? Now, hearth temperature is also important. Hearth temperature of the blast furnace. Why hearth temperature is important? How hot the lower part of the furnace is, where slag and hot metal is accumulated. So hearth temperature, hearth is the region where basically we are separating the slag from the hot metal. So obviously hearth temperature will be important because that will determine that how hot our slag is going to be. Fluidity of the slag. Now we talk about one very important criteria, which we call nothing but the fluidity of the slag. Fluidity of the slag. Now slag must be sufficiently fluid. That means low viscosity. Why it should be sufficiently fluid? Because if it is not fluid, then it cannot flow quickly through the coke bed and it cannot be drained out through the slag notch. So these kind of problems we will face. So fluidity of the slag is very important. So you can just simply say that the slag must be sufficiently fluid. The slag must be sufficiently fluid. Okay. If the slag is viscous, a lot of problems will be there. Reactions and slag composition is also important. At higher temperatures, the CA calculation. Okay, let us write and then explain. Reactions and slag composition. Okay. So reaction and slag composition, if I'm talking at higher temperatures, what happens? what happens at higher temperature? As the temperature is high or at higher temperatures, lime, like calcium carbon, TOC, CaCO3, it decomposes completely. Decomposes completely to calcium oxide plus carbon dioxide, right? This will happen. And CaO, calcium oxide reacts fully. Calcium oxides reacts fully with SiO2 and Al2O3 to form stable compounds. To form stable compounds. Okay. So Hearth temperature affects the fluidity or the viscosity of the slag, degree of reaction completion, distribution of oxides with slag. So you see, Hearth temperature, why it is so important? Hearth temperature affects. What are the things which are getting affected by the Hearth temperature? One is the slag fluidity. This is going to be affected by the Hearth temperature. Degree of reaction completion. And distribution of oxides with slags. Okay, and ease of tapping and furnace stability. So these all are being determined by the earth temperature, right? Now we will basically talk about some very fundamental things. Okay. We have covered a substantial portion. Now you need to understand one thing. The slag volume should be less. We do not want a lot of slag to be there. So, in the summary, you can just summarize whatever we have discussed in this manner, that high slag volume is not required. High slag volume it means what it means? It means bad for economy. So, it is not economical. High slag volume is not economical because more fuel consumption to melt extra slag. There is going to be more fuel consumption to melt the extra slag. Okay. So lower productivity, it is going to hamper the productivity. Well-designed slag is something which we need, good furnace operation. So well-designed slag is going to help us in achieving good furnace operation. And proper basicity requirement is also maintaining proper basicity of the slag is also something which is very much required because for proper removal of sulfur and phosphorus. Okay, so maintaining proper basicity of the slag. Maintaining proper basicity of the slag. Okay, which is good for sulfur and phosphorus removal. And optimum viscosity. Optimum viscosity. The slag must be viscous, but not very much. Okay, not very much and not too less also. For basically smooth flow and perfect separation from metal. Smooth flow and perfect separation from metal. Right? Now we talk about the composition of the pig iron. Now we talk about the composition of the pig iron. So when we talk about the composition of the pig iron, so pig iron means it's crude iron tapped from the blast furnace before refining. That is what is basically pig iron. So it is the crude iron which is directly tapped from the blast furnace before refining. Okay. So it contains high amounts of carbon with multiple impurities, right? It is having a lot of impurities. Let us now see the elements which are mostly there in the pig iron, and we will also look at their percentage range. Okay, followed by the role or effect. So we'll see this. So element, suppose I am talking about carbon. So what is the range of carbon, percentage range of carbon in the pig iron? You will get 3.5% to 4.5% carbon in the pig iron. So definitely you can understand one thing that why so much carbon is coming. That is because of we are what is our main reducing agent in the blast furnace? The main reducing agent is the coke. So from the coke only this amount of carbon is coming. But its role is it has got a good role. That is, it increases the hardness. It increases. Okay. So let us see. I was talking about the elements, right? So carbon. Right? The percentage range is 3.5 to 4.5%. And what is its role? It increases hardness and brittleness. So you can understand one thing that obviously uh, the amount of carbon has to be reduced, because if this amount of carbon is there, uh, then obviously it is of not much use. So in the steel making, our main objective is going to be to reduce the carbon content. Okay. From the carbon, now we will see the silicon. The silicon is basically 1 to 3%. The silicon is basically 1 to 3%. Okay. It improves fluidity. Silicon improves fluidity. It improves fluidity, reduces the melting point, reduces melting point. Okay. And but too much of silicon is also bad, because it causes brittleness. So silicon, if it is too much, then it causes brittleness. Okay. Now manganese, if I'm talking about manganese, then manganese is basically 0.3 to 1.5%, right? Uh, it Now manganese, why manganese is very important? Manganese, some form of manganese is good. Okay. Why? Because it removes sulfur. Manganese helps in removing sulfur, and it also increases hardness. And it increases hardness also, right? Now, sulfur. Now, if I talk about sulfur content, the sulfur in the hot metal, there is going to be, or the pig iron, there is going to be some portion of sulfur. We cannot help it. 0.03 to 0.08%. इतना सल्फर तो रहेगा ही रहेगा. This amount of sulfur will always be there. And this is actually highly undesirable. Sulfur is highly undesirable. Very bad actually, sulfur for the steel, and causes hot shortness. So this also you should remember, that what is the problem which is caused by sulfur. So sulfur causes hot shortness. Hot short, right? So this is the thing. Okay. So we have covered substantially with this the iron making part. So the hot metal composition, you should remember the hot metal composition. Okay. Means remembering is not that important, but range at least we should have an idea, like carbon, in what percentage carbon is there, what percentage silicon is there, what is the range for manganese, and what is the range for sulfur, and what are their role. I think this class was very helpful, and please subscribe MetaGate for more such classes, because in MetaGate, this is a one-stop solution for all the metallurgists, and we are always focused on delivering the best to the students, and that is the main idea of MetaGate, and that is why we are making this kind of initiatives to make these lectures free in the YouTube so that most of the students can get benefit from it. Thank you. Stay with us.